Hi there, James here, going to help you with this derivative problem. So we're given some original function and we're asked to evaluate the derivative of the inverse of this function at some value. So right off the bat, if we could just get the inverse of this function and take its derivative, right, we'd be done. But unfortunately, we can't. And the reason why is because this function's inverse is not itself a function. So that puts a kibosh on that real quick. So let's revisit what it means for a function to have an inverse. So if you have some function, f of x equals y, it's going to have a set of points, x comma y. Well, to go from a function to its inverse, you just switch the x's and the y's. So we know an input into our inverse corresponds to an output of our original. So this input of -2, that's really code for an output of -2 into this original function. So we can get that x value or that input that's going to give us an output of -2. Now this part has to be easy because if we couldn't find the inverse right off the bat, then we'd be stuck right here. So sometimes you can solve these explicitly. But in general, you'll be able to solve them very, very quickly by just testing really nice values. Zeros or ones, kind of keep your eye out for the domain on this. If your original function is a natural log function, test something that has an e in it, like e to the first or e squared. But the point is getting this is not meant to be hard. So we have a point 1 comma -2 of our original, which corresponds to a point of -2 comma 1 in our inverse. So this idea of input to one or the output to the other is really helpful when it comes to calculus too. When we're thinking about the derivative, we think of dy dx. Well, if we just switch the x's and the y's, right, this change in y over change in x really corresponds to a change in x over a change in y when we're talking about our inverse. So this gives us that roadmap of what to do next. If we get dy dx, we just need to reciprocate it, and that's going to be the slope of our inverse at the corresponding point for this, that point being -2 comma 1. So f prime of 1, it's really easy to get a value of 10, reciprocating it because we want dx dy will give us the slope of this inverse, not function, of this inverse at that corresponding input of -2. Now there is a formula for this. I do not recommend it. It's hideous. You still kind of have to do this idea of back solving for this corresponding point, or getting the output given some input. So that formula is not my favorite. Doesn't really lead to things being shorter, and it's not the prettiest formula. I know, dare I say, sacrilege. It's not a user-friendly formula. How about that? Before I get out of here, I just want to show you guys a visual using a lot easier functions. So if we were to look at x squared for x being greater than 0, so that's this green, half a parabola right here. When we're talking about its inverse is also a function, just because I restricted this to only be half of a parabola. So on our original, if we have a point 2 comma 4, that corresponds to a point of 4 comma 2. And then this idea of the slope of the tangent line at that point is rise over run, or change in y over change in x, just happens to be instantaneous. Then what used to be our rise on our original is our run on the inverse, and then vice versa. So that to me helps with this idea of, oh, that's why I'm getting the reciprocal of dy dx, because the x's of one are the y's of the other. The other thing you see in the graph that's really nice too is just the symmetry along the line y equals x. And that's because, well, that's a symmetry a function has with its inverse, or at least what every relation has with its inverse. So function not even being required there. Well, anyway, good luck. And then you skip the formula. All right, have a great rest of your day.